Okay. So, number one, use the table above to estimate the total distance traveled at t equals 15. Okay. All right. Now, a lot of you probably, on number one, probably plotted these points, right? Is that my guess? No? You didn't? Okay, well, I'm going to do it, and then I'm going to show you the correlation between it. You really don't have to, but I do want to make the connection. That's why I'm doing it. Okay, so 5 is there. 10 is 18, so maybe there. Shh. It's fine. 15 is 10, so something like this. Okay, so maybe the curve connects these somehow. We don't know how it connects, right? Because remember what I said, tables don't give us all information, it just gives us points on the graph, right? The curve could be going crazy. But those are the only points we have. And if you want to visualize a curve, that's fine. But first thing you have to know is how many subintervals do you want? You want 3 subintervals. How wide is the whole thing? The whole interval is 15, because we're going from 0 to 15, right? So how wide is each subinterval? 5 units. And so conveniently, I gave you the data points for each, right? If this was 4, it'd be kind of weird to do because they wouldn't be equal subintervals. Okay? So that's that. So we're going to draw vertical lines to get our rectangle started. Okay? We know that the width of each rectangle is 5. And the way we express that work is we would say the total interval divided by 3 subintervals, which is 5 each, right? Now, the next question is, what is the height of each rectangle? What type of approximation are we doing? A right hand. So you have to go through it step by step. Don't try and overassume or overthink. It's actually very simple. In this rectangle that I'm going to form, you have a curve where this is the end of one of the rectangles, and this is the other end, in a sense. Which one of these points should I be using to determine the height? The right hand, because it's a right hand approximation. So that means I'm going to draw my rectangle so it hits this point, not this point. And which way am I going to draw it? To the left, because I want this rectangle. Does that make sense? Okay. Now we go on to this rectangle. All right, am I going to use the point to the left or the point to the right? To the right, because we're doing right hand approximations. And what about this one? To the right again, right? Everything's to the right because you're doing a right-hand approximation. So now we're going to figure out the area of each one. It's going to be what? 5 is the width of the first one times 21 plus 5 is the width of the second one. Some students will want to say 10 because the 10 value is there. That's not the case. It's how wide is the rectangle. So it's the distance between 5 and 10, not the coordinate. 5 times 18 plus 5 times 10. And then we figure it out from there. That's 105 plus 90 plus 50. So it's 140, 245. Okay, now, what did I just find there? Remember, there's 2 types of questions that I could ask here. I could ask for the distance traveled or the location or the position of where it's at, right? What is this? This is the distance traveled. Okay. What would I need to find the position? The starting point, the initial condition. What am I asking for? Distance traveled. Was there any units on here? No. So the answer is 245. Okay. Now let's try and understand that in terms of the table instead of the graph, because you got to be able to quickly do this. So let me rewrite the table real fast. T and V of t. And the other thing is, be careful here. Make sure the graph or the information I gave you was velocity. Distance is only going to be given or found when you have the velocity information, right? If I give you the distance information, if this was, just as a side note, if this was the position and you started at home or something like that, and the numbers were 10 there, how far did it travel at t equals 15? 10, because this is the distance traveled, right? So make sure you're talking about speed or velocity in this case. Okay, let's look at this in terms of the table so you can kind of see what to do in maybe an easier way. If I'm cutting this table into 3 equal subintervals, again, how wide is each subinterval? 5. So really, what we're doing is we're saying this is one rectangle, this is another, this is another. You guys see that? So this rectangle is how wide? 5. And then which one do I use? I use the right-hand one. 5 times 21. This is the other rectangle. How wide is it? 5. Which height do I use? 18. This is the other rectangle. How wide is it? 5. How tall is it? I use the right-hand value, so 10. So it's the same thing. It's just actually a little easier to look at on the graph, on the table. You get that? But you have to be able to know how to draw it on the graph too. So any questions? No? Number 2. You guys were all dying on how to take a derivative. There was an easy way to do this. Did anybody know the easy way?
Yeah.
Erica, maybe?
You do ln of the top.
You could do that, yeah. Using the rules of logs. If you know your Algebra 2 stuff, this problem is really easy. But I'm going to do it the long way because I want to make sure you're good. If I'm finding dy dx, I'm just taking the derivative. What is the derivative of log? What did I tell you to deal with log? I told you to put ln of a to the sine x over ln of a, right? You rewrite it. Now, the natural log of a is what? It's a constant, so I'm going to rewrite it as 1 over the natural log of a times the natural log of a to the sine x. You guys follow me? Now, this is a constant, so ignore it. What is the derivative of natural log of anything? So it's 1 over a to the sine x. And then times the derivative inside. What's the derivative of this kind of, what kind of function is that? So what's the derivative of exponential? Natural log of the base. So we're looking at this piece right now. Natural log of base times the function, right? And then times the inner of that. So a lot of chain going on. And then we saw this constant over here, right? So 1 over natural log of a. So simplify. The natural log of a, the natural log of a go away. A to the sine x, a to the sine x go away, and you're left with cosine of x. Okay, obviously the quicker way would be to rewrite it as sine of x times the log base a of a. What is log base a of a? It's 1. It's a raised to what power is a? It's 1. So y equals sine of x. So y prime equals cosine of x. Boy. Okay. I do want to cover one more problem from yesterday, I guess. It's dealing with exactly what we're talking about today. Okay. It doesn't matter. You can put it on today's notes. Okay. So same type of thing, but it's going to introduce the idea of LRAM, RM, and MRAM. Okay. So the table above shows the velocity, and it gives you units even. Okay. In feet per second, in seven different points in time. I want you to estimate the distance the particle travels using a left hand, a right hand, and a midpoint rectangular approximation. With 3 subintervals. Now, if I'm cutting it into 3 subintervals, how wide is the whole distance? 360. So how wide is each subinterval? 120. So our rectangles are actually going to go from what to what? 0 to 120. And 120 to 240. And 240 to 360. So if I'm looking at this rectangle right here from 0 to 120, again, how wide is it? 120. If I'm doing a left-hand approximation, which value am I using? Am I using the 24, the 30, or the 28? I'm using a left hand, so I'm using the left hand number, right? If I'm using a right hand, which number am I using? 28. And if I'm using a midpoint approximation, I'm going to use 30. And the only reason you could say that's the midpoint is because 60 is exactly in the middle of 0 and 120. Does that make sense? So take some time and try and come up with the answer on these three, okay? Give me equations, though. Or give me at least your string of numbers that you're adding up. Okay. So let's see if you guys got the answers right, and then we can go over them afterwards. LRAM was 9,360 feet. RRAM is 9,600 feet, and MRAM is 10,080 feet. Do I need to go over any of those? I hear midpoint. Do I have to go over all of them? Mid and left? Okay. So what does this really mean? LRAM. Left hand rectangular approximation method. Okay, and we'll get to all that. Okay, so we're going to do a left-hand approximation. LRAM is how wide is the first subinterval? 120. How tall is the first subinterval? We're looking at the height value to the left. So that's 24. Some of you guys are still saying the 24, the 30, and the 28, the bottom row, is your time interval. No. That's not the base. I know what the tendency is. Since it's the bottom numbers, it must be the base. No, oftentimes in tables, the top number represents which axis? The x-axis, which means the top number is your base lengths. Okay? So 120 times what for the left hand? 24. Plus, what's the width of the second interval? We're going from 120 to 240, so it's 120 times 28, because we're doing left hand, plus the distance from 240 to 360 now, 120 again, times 26. And so that's whatever that says, 9,360. Okay. MRAM means we're using the midpoint value to determine the heights of each rectangle. So what is the width of the first rectangle if I'm cutting it into 3 subintervals? 120 still. What is the height? I'm using the midpoint value, which is 30, plus 120 again times, what's the midpoint value between 120 and 240? It's the 30, and then plus 120 times 24, which is 10,080. Erica, you always say something like you want me to hear, and then when I...
That's like, I don't get it. Why do we need to know, like, the mid?
Yeah, because I'm asking, that's why. No.
It's confusing. Like, I can get why we would...
Because you would look at maybe a situation and say, this is the only data I have, which one of these methods would produce the better answer, the more accurate answer? And a lot of times the midpoint value is the the better answer. You just have to determine it based on what's given. Okay, so that's that. Now, let's continue on in our adventure of calculus. Now we'll put some words to what we've been doing, okay? There's where it comes from. Rectangular approximation. So you have left hand, right hand, and midpoint, okay? So it estimates the area under a curve by dividing it into rectangles, just like what we talked about yesterday. Okay? And finding the area of each rectangle and then adding it up. All right. So when we say left-hand approximation, we abbreviate LRAM. Okay? It uses the left-hand points on the function's curve within that rectangle. You look at the rectangle, you look at the points that determine the heights, and you use the left-hand one, right? So let's take a look at this function, y equals rad x, from 1 to 4 using 6 subintervals. What are we going to do? Type in your calculator, maybe. Actually, let's do this by hand. Let's not use our calculator. Let's do this. We have 6 subintervals. And what is the total interval? 3. 3. So,
Oh, so you do it at
how wide is each subinterval?
like 0.5.
It'd be 1/2, right? If I'm starting at 1 and going to 4, the whole length is 3. And we are cutting it into 6 pieces. So that means each piece is 1/2 or 0.5, right? So let's quickly create a table here of x and y values. What's the first x value?
1.
Okay, 1, yeah, thank you. What's the second x value?
3/2.
And don't do 3/2. 1 and 1.5. The next one? 2, 2.5, 3, 3.5. How far are we going here? 4?
4.
Okay, so that's that. Now we need to figure out what these y values are.
1.
So what is the y value when x is 1?
1.
How do you know that?
Rad 1.
Because the function is y equals rad x. So it's just, I'm gonna do it like this. I'm gonna say rad 1. Because you can say 1, but do you know the square root of 1.5? So I'm gonna call it what? The square root of 1.5. What's this one gonna be?
Rad
Square root of 2. I'm just trying to get you the method to solve the problem, not get the exact answer anyways. What's this? Rad 2.5, rad 3, rad 3.5, rad 4. Okay. Now we are doing a what? Left hand. And how wide is each subinterval?
5.
So we're going to say 0.5 times, which value do I use? The left, so rad 1. Plus, how wide's the second one? 0.5 times rad 1.5. Plus 0.5 times rad 2. Plus 0.5 times 2.5. Plus 0.5 times rad 3. Becomes very repetitive, right? And if you heed my warning from yesterday, what do you have to make sure when you're all said and done? That you have 6 subintervals, because you're going to keep going, and then you're going to go, okay, I'm done, and then you're going to have 1 too many. Okay? Because this last one here, this 0.5 times rad 3.5 is which rectangle? It's this last one, right? And so that determined the height of the last rectangle, which means we're not including this. Okay? And count. 1, 2, 3, 4, 5, 6. There's that. That's fine. Without a calculator, could you simplify this in any way?
You could, like, the rad.
Factor out a 0.5, right? Okay. The other thing is, on the AP exam, if that's what it's asking you to do, you're done in terms of simplifying it. On the AP exam. Okay. But I'm going to factor out a 0.5 on all these, so you end up with rad 1 plus rad 1.5 plus rad 2 plus rad 2.5 plus rad 3 plus rad 3.5. That's it. Okay? And then you can maybe simplify it further than that, but we'll call it done at that point. Notice I could only factor out a 0.5 because all the subintervals are equally divided, right? If I give you a table where they're not equally divided, you can't factor out that common factor. And sometimes that you run into that issue. Okay? It'll say use 3 subintervals using the indicated points in the table. And so you have to figure out the width of each one. They're not going to necessarily be the same. So here's what the function looks like graphically, right? I'm going to draw my vertical lines. Looking at the first rectangle, am I going to use this point or this point for a left hand? This, and I'm going to draw to the right. So you can see what's happening here with those lines. An underestimation, okay. Do you think that's based on the direction of the function or the concavity of the function? We'll find out in a little while. Okay, oops. So there's that. So you guys can predict what's next, the right-hand approximation. Okay, it's the same thing, but we're looking from the right, and we're going to use the same function. So I want you to evaluate the same thing, but I want you to use right-hand approximations instead of left-hand approximations. Okay. Here, let's just do this. Oops. Okay, so give that a shot on your own. Okay, so what, did you guys get an answer for the right hand? No.
I got an answer.
It should be actually pretty easy. Let's look at the graph of it first of all. So there's the vertical lines. Looking at the first rectangle, which point am I using? The right-hand point. So it's going to be now, all these points are going to be above, right? Okay. So if I'm going to break this down, what is the width of the first rectangle? 0.5. But looking at this table now, what's the height? Rad 1.5. What's the width of the second one? 0.5. And what's the height? Rad 2. Are you guys okay with this? And you're going to repeat this all the way to the end, but which height are you going to use here? The rad 4. We're finding the area. Well, the graphical thing is we're finding the area under the curve. If this is velocity, the velocity function, remember yesterday we talked about that constant velocity function? And we showed that really finding the distance that a car travels is distance equals rate times time if it's constant. So it's just finding the area of a rectangle. So it's finding, if you find the area under the curve, the velocity curve, you're finding the distance traveled. If it's an application problem, this isn't. This is just find the area under the curve. Same context, or same thing though. All right, so check this out. If I'm doing a right hand, the work's the same except for two things. What? The first one's gone, and you add the last one. If you notice that, that's a good thing. You guys get that? That's a right-hand approximation, and then you simplify it from there. Okay. Okay. So you should have gotten something like that. Okay. Is there any questions on this? Is this pretty okay? It's pretty okay. It's not amazing, but it's okay. All right. Can I go on? Okay. Let's see what's next. Oh, so this is going to be comparing whether it's an over or under approximation. Okay? And sometimes you do want it to be strictly under, and sometimes you do want it to be strictly over. Let's say you have a budget, and you want to figure out, you don't want to exceed a certain amount, so you're going to want the under approximation every time, or vice versa, right? Okay, so that was a left hand. That's the right hand. The left-hand approximation, is the estimate going to be below the actual value or above the actual value? It's going to be below. And the right hand? Above. Okay? So, determine to be, let's see, over or under the actual area based on, I don't know, let's take a look. If I have an increasing concave down, that's that, versus an increasing concave up, versus a decreasing concave up or a decreasing concave down. Those are the four different types, right? Let's just look at one subinterval. I'll do two subintervals. Here's two rectangles, right? Two rectangles. Two rectangles. Two rectangles. If I want a left hand, let's just do left hand on all of it. Which point am I going to use? I'm going to use this point or this point? This one. This one or this one? Okay. This one or this one? That and that. I'm going to use this one now for left, right? And then this one. And then this one. And then this one. So a left-hand approximation, an LRAM, is under where? Which ones is it under? These two, right? What is in common about these two functions? They're both increasing. Is their concavity the same? No. So it's under on these. It's over on these. What's in common about these? It's decreasing, right? So it has nothing to do with concavity in a left hand or a right hand. Okay? It has to do with whether the function is increasing or decreasing. Now, I'm not going to put something in your brain that you have to memorize. You have to be able to visualize it. If I draw what's happening on the function, and if I can draw the rectangles how I'm supposed to, you should be able to observe if it's above the curve or below the curve. Does that make sense? Because if you're doing a left hand, you're going to get a different answer than if you're doing a right hand. You get what I'm saying? Okay. No, because here's a left-hand example. And the first point is above the second point. Not the x value is points lower, but the y value is point. Okay. So it all depends on whether the function is increasing or decreasing. So in a left hand, if the function is increasing, then it's an under approximation. In a left hand, if the function is decreasing, then it's over. Now let's look at right hand. If it's a right hand approximation and the function's increasing, then it would be here, it'd be over. And in a right hand, if the function's decreasing, then it would be under. Okay? So again, you have to be able to write that out. Okay? If you need to write it down and memorize it, that's fine, but you're just, you're filling up your brain with data that you can calculate on the fly if you need to. Okay? So the example I'll give you here is left hand on a strictly increasing function is an under approximation. What? Oh, decreasing. Left hand on a decreasing function is an overestimate. You guys okay with that? I'm waiting. All right, can I go on? Ready, set, cool. Okay. Oh, this one's a fun one. I like this one. Estimating volume. Oh, because you looked at the notes. You have to sit and admire my drawing more than anything else. It took me forever to come up with this drawing. So, if I'm estimating volumes, and we're going to get more in depth into this later, we can get some crazy shapes that we can find the volumes of, and figure out, how much volume we need in aluminum or whatever else to build something. Okay. So the formula for a volume of a sphere. Do you guys remember the volume of a cylinder? First of all. Cylinder. Pi r squared times h. Remember, it's the area of the base, which is a circle, so pi r squared times the height. Okay. Do you guys know the volume of a sphere? What's a sphere? Wait a minute. What's the sphere, first of all? It's a ball. It's a circle. But you can look at it this way. It's a circle that's doing what? And this is what we're going to do with this. This is kind of cool. It's a circle that's spinning. Right? This is going to be cool. Ready? This is going to be cool. Okay? So, we're going to estimate the volume of a sphere using rectangular approximations. And then eventually we're going to derive the volume of a sphere by using integrals and approaching infinite number of rectangles. Okay? Estimate the volume of a sphere with radius 4 by using 8 subintervals. First thing I'm going to do is understand the equation of a circle. You guys remember the equation of a circle? That's 1, x squared plus y squared equals 4. In that case, what's the radius? 4 squared, I should say. It's 4, right? Okay. If you graph this, or if you solve it, I guess, and then graph it, you should be able to observe this. You should have seen this from Algebra 2 or whatever. This is the graph of above the portion of the circle that's above, right? You guys okay with this? Now, before you go anywhere, hold on, okay? Just put your pencils down and pay attention to this, okay? So, we are trying to find the volume of a sphere, of a ball, by using this half circle. The half circle is x squared plus y squared equals 4 squared because the radius is 4. Now, we're cutting it into 8 subintervals. What is our total interval? What is our total interval? What are we starting at? -4 and going to 4. So what's our total interval? 8. If we're cutting it into 8 subintervals, how wide is each subinterval? 1. Okay. So now let's visualize this, okay? You're going to take a ball, and what we're going to do is we're going to slice it. What kind of shapes is it kind of making? What? A skinny cylinder, right? If I just slice off 2 parts, what are those 2 slices going to look like? No. A can of. No, but that's not my question that I was asking. Okay. So if I take a sphere, okay, and I slice it like this, okay, in a way, what is that slice? It's the 2 outside of it is circles, making it a cylinder, right? A can of cat food, right? In a way. Now we have little arcs at the top and the bottom, so it's not exactly a cylinder. But remember, the more we slice it, the more it resembles a cylinder. So watch this. Okay, so I'm cutting it like that. What I'm going to do. This is what were we doing? A left hand? Okay, we're doing a left hand, so in this little rectangle here, we're going from the left and going to the right. We're using the left hand point here, the left hand point here, and so on. Since the function is increasing in quadrant 2, the left hand is below the curve, but because the function is decreasing in quadrant 1, the function's above the curve, right? We just talked about that? Okay? Now what we're going to do is we're going to take these little rectangles and we're going to revolve them around the x-axis. Yeah, Taylor. No. Okay, so first of all, I came up with the vertical lines because we're cutting it into 8 subintervals, right? And then it said over here, we're doing a, where did it say? It didn't say. So I'm telling you right now we're doing a left-hand approximation. Yeah, because I said so. Okay? So in this rectangle, which point on the curve am I going to use? Am I going to use this point here or this point there? The left hand, because we're doing a left hand, right? And so we draw to the right. And then in this rectangle, we're going to use the left hand point. And so that's where it comes from. Is that okay? Okay. Now, we're going to take, yeah, there it is. There, I told you. LRM. Okay. We're going to take these rectangles and we're going to rotate them. If I rotate that rectangle, what kind of shape am I getting? Be patient, okay? It will develop and you'll see it as time. I don't want to just skip it all. Took me forever. Yeah, in a way, yeah.
Wait, did you draw that by hand?
Yes. It took me forever.
Why are you lying?
Do you see me erasing, like the animation that's erasing all the pieces that...
You copy-pasted that.
You can't. This program is all handwritten. That's why all this is in handwriting instead of typing.
I don't know, man. I hope you don't want to fake Rob. You're not wise for that.
But my point is, as it goes through, you should be able to start seeing what? Cylinders developing, right? I'm erasing all the pieces that are behind so you can see them more three-dimensionally. Eventually, it will end. We'll wait till we get to some crazy figures. It's fun later on. Okay? So, no, I have to because I want you to see what's happening. All right. Shh. So now you can see you have a bunch of cylinders that are kind of stacked up next to each other, right? And in order to find the volume of the sphere, that would be kind of equivalent to finding what? The volume of each cylinder and then doing what? Adding it up, right? So, what is the volume of a cylinder then? Pi r squared times height. Now in this case, look at this. Let's just look at this last cylinder as an example. It's probably the easiest. What represents the height? It is the distance this way, right? So how far is it on this? It's 1. So the height of each one of these cylinders is 1. Now what is represented by the radius, or what gives us the radius? The y value. So it's going to be this guy. Okay? So now, how many cylinders do I have here?
Oh, it's rotating across the...
How many cylinders do I have? It said right here 8, okay, 8. So here is the cross-sectional view, the two-dimensional view that might help you see it, okay? What is the width, or sorry, what is the height of this cylinder? 1, because these cylinders are standing on end, kind of, right? So the height of this cylinder is 1. It's kind of hidden over here. You can't really see it, but it's 1. And what is the radius of the cylinder? It's 0. So we're going to say the volume of each cylinder is pi r squared h. So that represents the radius, okay, because that's the y value. Okay, so let's break this down. Volume is equal to pi r squared times h. So here's our pi. The radius is the height of each rectangle. So it's 0 in this case because we're looking at the left hand. And then what's the height represented by? It's the distance, it's the subinterval, right? So that's the first cylinder. What's the second cylinder? What is the height of the second cylinder? It's this, right? What is the radius? It's this guy, right? Whatever. How do I figure out what that is? I plug in which value? -3 into this equation. And so you end up with rad 7, right? And that's squared. And then the height would be 1. What would the next cylinder's radius be?
Oh, wait.
Okay, so the radius is this height, right? So I plugged in -3 to my equation. So I plug in -3, I get 9. And then 16 minus 9 is 7, I square root it. So that's that. We actually did pretty good there.